Hello, eigenvalues and eigenvectors are quite an important topic of linear algebra. A lot of this has to do with a matrix. Here consider matrix A, which is multiplied by a non-trivial vector. Let's say you could write A times U and then express this in terms of the product, a scalar alpha times U. So the important thing here is that we are multiplying a square matrix times a column vector, and that equals to a vector that has a specific shape, a vector that's obtained by multiplying a scalar times a vector, and that's a scalar multiple of the same vector, right? So this still has that shape. What is required here is for this matrix to be square. And in writing this type of equation called the eigenvalue eigenvector problem or the eigenvalue eigenvector equation, it doesn't really matter what we use to denote the vectors. We can also write something like AV equals alpha V. We could also use another notation for scalar. Very common is AV equals lambda V, right? So it doesn't really matter, but the important thing is that we're saying there is a square matrix A, which multiplied by a non-trivial vector is that matrix vector product is exactly equal to a multiple, the scalar multiple of that same vector, and that's precisely what defines eigenvalues and eigenvectors. So now we want to say more about this important topic of linear algebra. We consider a set of eigenvectors corresponding to some eigenvalues. And the important thing here is that these eigenvalues are not identical. So that's exactly what we mean with this notation, that the lambda k is not equal to lambda j whenever k is not j. It means that this is telling us, that lambda 1 is not equal to lambda 2, and lambda 2 is not equal to lambda 3, and lambda 3 is not equal to lambda 4. That is because 1 is not equal to 2, 3 is not equal to 4, 2 is not equal to 3, and so on. Right? So this is saying that we have eigenvalues. This is a scenario in which the eigenvalues are not the same. Okay, these are eigenvalues that are distinct, if you will. They're different. There is no identical eigenvalues. Okay, so something that you could argue is related to multiplicity, but doesn't matter. We don't have to quote multiplicity right now. The key here is we have a square matrix. It has some eigenvalues such that they're not the same, they're not identical, and then we have a set of eigenvectors where each eigenvector corresponds to each of those eigenvalues that are distinct. And then the important thing of this theorem is that it tells us that the eigenvectors are linearly independent. Okay, they are linearly independent. This is a big deal. This set of eigenvectors are linearly independent. Also, what is being assumed here with this notation is that any vector xk is not the zero vector in Cn. Okay, so any of these so-called eigenvectors is not a trivial. These are non-trivial. Okay, non-trivial vectors in Cn. If you're multiplying the A matrix times the zero vector, you will obtain a vector of zeros, and that vector of zeros multiplied by any scalar is still a vector of zeros. So that's kind of like a trivial way of solving the eigenvalue eigenvector equation. And what I would like to do now is to discuss in more detail some of the technicalities that you would argue in writing a proof. And the proof of this theorem is by no means unique, and I'm not really going to write the full-fledged proof, but I'd like to share with you, I'd like to discuss some of the details of this proof, because we're going after linear independence. We'd like to prove that a set of vectors is linearly independent. So the linear independence is something that would be a linear combination. I'm going to use alpha to denote scalars, and say, for example, alpha sub I times x sub I equals 0 when this I is an index running from 1 through p. So this would be a linear combination involving all the vectors on the set, all the vectors in this set S. And so to address linear independence, we would have to say if this relation of linear independence is true, we would need to conclude that alpha 1 is equal to alpha 2, which is equal to alpha 3, which is equal to all the alphas, alpha sub p being equal to 0. We start with a linear relation of linear dependence and conclude that all the coefficients, all the scalars are 0. That would give us independent, linear independence. But instead of going that route in which we involve all presently mentioned eigenvectors, I'm going to go and work with 2 of these eigenvectors at a time. So first, we're working here. Let's suppose we're working with 2 of these eigenvectors. They don't have to be consecutive. So suppose we have indices j and k such that they're different. Okay, so we have 2 different indices such that lambda sub j is not equal to lambda sub k. That is because we're assuming all eigenvalues are different from each other. And because these are eigenvalues, then we have that a times x sub j. Okay, so suppose we have 2 different indices, 2 different eigenvalues. So the matrix multiplied by the eigenvector xj equals lambda j xj. Okay, and also the matrix multiplied by x sub k equals lambda k times x sub k. Okay, so that's what it means for those lambdas and those x's to be eigenvalues and eigenvectors. Now let's consider a relation of linear dependence involving xj and xk. So let's consider alpha j xj added to alpha k xk, and we consider this as being a relation of linear dependence. This equals the 0 vector in Cn. Okay, so I'm going to consider this relation of linear dependence, and I'm going to call this equation 1. So here is that relation of linear dependence, alpha j xj, alpha k xk, and this is equal to 0. So what I do next is that things are kind of, I'm moving, sliding this down, so you need to see the statement of the theorem. You can rewind this, but so I'm going to slide this down a little bit, and so some of those part of the statement of the theorem will be less visible. But what I did in the next step, departing from equation 1, was to multiply on both sides of equation 1. Remember, this equation 1, this is a 0, but this is not the 0 scalar. This is the 0 in Cn. So I multiply on both sides of this vector equation by the matrix A on the left side, in each term on the left side, by multiplying this linear combination by A, multiplying the matrix A on the left side. Then I end up with these terms here. This is very simple. The matrix times the 0 vector is the 0 vector. And what I do in intermediate steps of this product is that I can pull the scalars alpha j up front, and so I have alpha j times a times x sub j, and then I have alpha k times a times x sub k. That's for the left side of the expression 1, and the right side still remains as the 0 vector. And then I use the definition of eigenvalues and eigenvectors, right? So we had we were assuming that precisely lambda j and xj satisfy this equation, so we could substitute, we could make a substitution and so this part is going to become lambda j xj because of the definition of eigenvalue and eigenvector in the sense of xj and lambda j, and then this portion also using that definition becomes lambda k xk. So I still have a linear combination. Here is alpha sub j, here's alpha sub k, okay, and this linear combination is still adding up to 0. So I'm going to call that linear combination, that relation of linear independence, still being a linear combination, equal to 0. I'm going to call that number 2. But let's keep in mind that we still work with number 1. I'm going to say something. I want you to compare 1 and 2. There are things in 1 and 2 that look very similar, okay? And I want to get rid of one thing. And to get rid of that one thing, I'll do the following. I'm going to take expression 1, and I will multiply expression 1 by the scalar negative lambda j. Okay, I do this, and by doing that, I end up with minus alpha j lambda j xj minus alpha k lambda j xk, and multiplying 0 vector, the 0 vector times minus lambda j, I still have the 0 vector. So what we do next is that we add that expression to expression number 2, and by doing that we can notice that in expression number 2 here, the first term, we have alpha j lambda j xj. That's precisely what is a negative term here, and that's going to go away. So adding that expression to number 2 leaves us with the expression alpha k times quantity lambda k minus lambda j, doing some factorization, times the vector xk. And here's the important part. The important part is that we know that xk is not the 0 vector, and we also know that lambda k minus lambda sub j is not the 0 scalar, because we had assumed that both of these quantities are different from each other. They're not equal, therefore their difference is not 0. So since the vector is not the 0 vector and the difference of those two eigenvalues is not the 0 scalar, then this implies that alpha k has to be equal to 0. So what we do next is now go back to the expression 1, multiply that expression by minus lambda k. That gives us a new expression, alpha sub j lambda k x sub j minus alpha k lambda k xk. And then what we're going to do next is we're going to add that expression to expression 2. And in doing so, we will obtain alpha j. We will obtain alpha j times quantity lambda j minus lambda k times the vector xj equal to 0. There are things that cancel out here, and so this, similarly as before, this implies that alpha sub j equals 0 precisely because we were assuming that lambda j is not equal to lambda k, which means that when you consider the difference of these two things, that difference is not 0. Okay, we're also assuming that that vector is not a trivial vector, and therefore that leads to the conclusion that the scalar alpha j has to be 0 to make this vector equation true. So this is the argument you would use. You would have to repeat this, but this is the essence of the argument to derive linear independence for the eigenvectors corresponding to eigenvalues that are not identical.